Hello, dear students. In continuation of the topic molecular orbital theory for heteronuclear diatomic molecules and polyatomic species, today we are going to learn a comparison of homonuclear diatomic molecule and heteronuclear diatomic molecules. Before that, since from 4 to 5 video lectures in last week, we saw some basic concept which required to understand the molecular orbital theory. There we saw that how molecular orbital theory is important to understand the formation of molecule with the help of some concepts of valence bond theory. Now we discussed that there are different molecular orbitals depending upon the type of atomic orbital taking part. So we have sigma, pi, delta, omega. These are the molecular orbitals. Like ASPDF, these are the atomic orbitals. Now in molecular orbital theory, to understand the formation of molecules, we need to write their MO diagram. So MO diagram is very important. Those who know about the MO diagram because it is not new for you, because we already discussed, or you might have learned in a last year of second year of BSc for a simple diatomic molecule. But as we know that one of the feature of MOT is that it helps to understand the formation of molecule with orbital overlap of atomic orbitals. So here when two atoms of same elements contribute their atomic orbitals in a valence shells which contain unpaired electrons, when they taking part for the formation of molecules, so these atomic orbitals should have same energy which is mentioned here. Suppose here 1s orbital of one atom and another 1s orbital of another atom, both having same energy, and that's why they mention in a same level in a energy profile diagram or MO diagram. Same way, when 2s orbital overlap, or when 2s orbital of two different atoms combines, they must also have the same type of energy levels, which is same for 2p orbital also. So once this 1s atomic orbital of both atoms when combines in this fashion, there is formation of one bonding molecular orbital called as BMO, and other is a antibonding molecular orbital called as ABMO. So here when 1s orbital overlap with another 1s orbital, that overlap is an axial overlap which result into formation of sigma 1s bonding molecular orbital and sigma star 1s antibonding molecular orbital. So this is the label of sigma 1s and this is the label of sigma star 1s antibonding molecular orbital. Same type of combinations you can see when 2s orbital of one atom overlap with 2s orbital of another atoms. So again there will be two atomic orbital combined, so two new molecular orbital will get formed. One will be bonding, other will be antibonding. So bonding molecular orbital is labeled as sigma 2s and antibonding molecular orbital is known as sigma star 2s. Everybody understood? Is it clear now? Similarly, when 2p orbital of one atom overlap with another 2p orbital of another atoms, if both having same electronegativity, that means if both having same type of elements, then again 6 new molecular orbital will get formed due to combination of 6 atomic orbitals. So out of half, that means 3 will be bonding molecular orbital and other half that will be antibonding molecular orbital. ABM. So sigma to pz, pi to px, pi to py, these are bonding molecular orbital. Pi star to px, pi star to py, pi star to pz, these are antibonding molecular orbital. So when you draw all these molecular orbital with increasing energy level, then you can understand that the MO diagram, because MO diagram is the basic of molecular orbital theory. It is the base of molecular orbital. Those who understand MO diagram, so I request all students to draw this diagram, to practice this diagram 2-3 times in a notebook, so that you will remember whole the concept of MO diagram. Now, in last video lectures we saw the application of this MO diagram for the formation of some smaller diatomic molecule like H2 molecule, He2 molecule, N2 molecule, B2 molecule, C2 molecule, F2 molecule. So all these molecules are a simple diatomic molecule. Why they are called a simple diatomic molecule? Because all these molecules having elements, that elements are belongs to the second row of periodic table. So in these examples where only 3 orbitals mostly contributed, one is 1s, second one will be 2s, and third one will be 2p. So these 3 orbitals mostly we are using for the formation of molecular orbital in simple diatomic molecule. But now when you coming to the point like heterodiatomic molecule, then what is the MO diagram? What will be the difference between that? Or what will be the difference between MO diagram of simple diatomic molecule and heterodiatomic molecule? So dear students, today we want to learn that what is the comparison between these two molecular, or what is the comparison between the two type of molecules. So we will see that. So now topic of our discussion will be comparison between homonuclear diatomic molecule and heteronuclear diatomic molecule. Okay. So we will see here first homonuclear diatomic molecule. What do you mean by homo? Tell me. Homo means same. The molecules having 2 atoms of same element. Yes, again repeat. The molecules having 2 atoms of same elements are called homonuclear diatomic molecule. That means those molecules like C2, B2, N2, O2, all these are the examples of homodiatomic molecule, because both atom in that molecule is of same element. For example, O2 molecule. In O2 molecule there will be 2 oxygen atom, and that 2 oxygen atom belongs to the same element, that is oxygen. Same for C2, B2 and so on. Here when these atoms come closer to each other, at that time what happen? Their atomic orbitals approach to each other. At one stage they will get overlap, means they will get combined, and there is formation of molecular orbital. But as I said, whatever the number of atomic orbitals combines of that both atom, same number of molecular orbital will get formed. So here 2 atoms, atomic orbitals of atom when combined, there will be formation of 2 molecular orbitals. One will be bonding molecular orbitals and other will be antibonding molecular orbitals. Now in a homonuclear diatomic molecule there is a symmetrical distribution. Everybody understood? Why? Because same size atoms are there, same electronegativity will be there, and therefore there will be a symmetrical distribution of electric charge, as well as such molecule has center of symmetry. That example we already discussed, right? For example, if I have Cl atom, when you join by covalent bond, that bond is a sigma bond, that molecule is called as a Cl2 molecule. So in this type of example where the distance between the two Cl atoms. If you see exactly at center, that will be the half of that whole bond length between two Cl atoms. So that point where two Cl atoms are far apart from each other, that point is called as a center of inversion or the inversion center. Also, G and U properties are used to describe such molecules. G means G-red and N means U means unG-red. So G-red and unG-red properties are also described by this example. Now, mostly, as I said in just few minutes before that, the elements of second period of the periodic table forms such a simplest homonuclear diatomic molecules. So these simplest homonuclear diatomic molecules of second period of the periodic table involves 1s, 2s and mostly 2p atomic orbitals for the formation of molecular orbitals. So this is just how we have the homonuclear description of homonuclear diatomic molecule. Now let me see something about heteronuclear diatomic molecules. For heteronuclear diatomic molecules, again in definition you can see that when two atoms of different elements combine, there will be formation of heteronuclear atomic molecules. So at this case, when two atoms are of different element combines, at that time you know that the atomic orbital of such atoms will have different energy. That means which will be not of a same shell, but they are of different shells, and therefore their energy will be also different. But here in this molecule there is an unsymmetrical charge distribution you can observe. So that unsymmetrical charge distribution which is due to difference in the electronegativity of that two atoms which are going to combine. So here G and U terms we cannot apply because there is an unsymmetrical distribution of electron takes place. Now for heteronuclear molecules there will be different from the homonuclear atomic molecule because of three important points. One is called as two atoms of different electronegativities. Second one is that they have different exchange energy, and third one, the contribution of atomic orbital towards molecular orbitals will not be same. So how these three factors which differs the heteronuclear molecule from homonuclear diatomic molecules. So here we will discuss that three. Now the effect of different electronegativities. First point will be effect of different electronegativities. As I said just few minutes before that, for heteronuclear atomic molecules, two atoms are of different elements. When they combine, these two atoms have somehow different in electronegativity. For example, the electronegativity of carbon on the Pauling scale is 2.6, while that of oxygen it is 3.5. Pauling scale, Mulliken scales, these are the different scales used to define the electronegativity term. So according to Pauling scale, carbon having electronegativity value 2.6, while oxygen having its value 3.5. Now here the atomic orbital of more electronegative oxygen atom will be lower energy level as compared to the atomic orbitals of less electronegative atom. So that means when you draw MO diagram of such a heteroatomic molecules, then you can just keep this thing in mind that the atomic orbitals whose electronegativity value is lower or less, that can be shown in upper position as compared to those atoms of an element which are more electronegative. For example, oxygen, whose energy levels are lower as compared to a less electronegative element. Thus, when such atomic orbital combines, the resulting bonding molecular orbital will be formed in such a way that the bonding molecular orbital resembles the atomic orbitals of more electronegative atom because it is nearer to that. So I will show here how, while anti-bonding molecular orbital looks like atomic orbitals of less electronegative atom. So this is how we will see here. Suppose I have, this is a carbon atom, this will be oxygen atom, and these are the energy levels of carbon atoms and oxygen atoms. Let's say this is 2s orbital of carbon and this is a 2s orbital of oxygen. So you can see here energy levels of carbon is higher than the energy levels of oxygen. So when these two atomic orbitals combine, there is formation of two molecular orbital. One will be bonding molecular orbital, another will be anti-bonding molecular orbital. Right? So sigma 2s and sigma star 2s. So here when you can see this bonding molecular orbitals is very nearer to this atomic orbital, which is the atomic orbital of that oxygen. Oxygen is more electronegative. So those atomic orbital which are of high electronegative oxygen atoms, they mostly form the bonding molecular orbital, while the less electronegative atoms atomic orbital mostly form the anti-bonding molecular orbital. That thing you have to keep here in mind. Again I will revise. Those molecular orbitals, mostly bonding molecular orbitals, are formed when those atomic orbital of more electronegative elements, they are taking part in a bonding molecular orbital, while the atomic orbital of less electronegative atom, which are very nearer to the anti-bonding molecular orbital energy level, so they form the anti-bonding molecular orbitals. The bonding electrons spend more time near to nucleus of more electronegative element. This is the main reason that distortion of electronic cloud towards the nucleus. As I said, molecular orbitals are polycentric. That means it contains two centers or more than that also. So if I have a simple diatomic molecule like these, there is an equal distribution of electron cloud over the two nucleus takes place. But here when you say in a second diagram that there is like a carbon monoxide, there is an unequal distribution of electron taking place over that nucleus, again because of a difference in electronegativity of two atoms. That you have to keep in mind. Now, effects of covalent bond energy. This is second important difference, that how they are differ. In a homonuclear atomic molecule, the atomic orbitals of similar atoms have same energy levels. Hence, bonding molecular orbitals lower energy levels than the atomic orbitals from which they have been formed. As I said just few minutes before that, in a MO diagram, you just see first, second, third in the picture. That the first one is a homonuclear molecular MO diagram of homonuclear diatomic molecule. Second one is a heteronuclear diatomic molecule, but there is a less electronegativity difference. And third one is again of the same type, but there will be high electronegativity difference in the heterodiatomic molecules. So in homonuclear diatomic molecule, the atomic orbitals of two atoms of same element, when they combine, the bonding molecular orbital form have lower energy than the atomic orbitals which have been combined. The difference in energy level between these two is called as exchange energy or delta E. So the difference that you have to count. and it is maximum for it is maximum in a homonuclear atomic molecules. But in heteronuclear atomic molecule, if you look at that, distance is decreases or it is reduced because of atomic orbitals are not of the same energy, hence there will be reduction in energy takes place. If the energy difference between two atoms is very large, that means there will be very less delta E. At that time, covalent character of such molecule goes on decreasing. So that you have to keep in mind about the exchange of covalent energy. Now, third important point, that contribution of atomic orbitals towards molecular orbitals. So in homonuclear atomic molecules, the atomic orbitals of two combining atoms are at same energy levels. We just revise that again. The atomic orbital, the homonuclear atomic molecules, the atomic orbital of two combining atoms are at the same energy levels and they contribute equally in bonding and anti-bonding molecular orbitals. So psi b is equal to what? Wave function of bonding molecular orbital is equal to wave function of atom A plus a wave function of atom B. That means there will be addition takes place. But in anti-bonding, there will be subtraction takes place between two atomic orbitals. Psi A is equal to psi A minus psi B. But for heteronuclear atomic molecule, the contribution of atomic orbitals towards the MO is not identical because of difference in electronegativity. And therefore, there one important factors comes into the picture, that is called as a coefficient of atomic orbitals. So, by putting that difference of electronegativity in the equation, then you will get psi b is equal to x psi a plus y psi b, and for antibonding psi a is equal to x psi a minus y psi b, where x and y are called as coefficient of atomic orbitals, and y is always greater than x for heteronuclear atomic molecules. Thus, for heteronuclear atomic molecule, there is unequal distribution of molecular orbitals taking place, resulting in the formation of new molecular orbitals. But here, students, you have to keep one important thing, that is this ratio. The ratio of y upon x is a measure of polarity. As we use the words commonly word, that is a polarity. Polarity is what actually? It is a difference in the electronegativity of two atoms. So the ratio of y upon x is the measure of polarity of molecule, and therefore for homonuclear atomic molecules, x is equal to y. That means there will be difference in electronegativity 0 between two atoms of an element. At that time, y upon x is equal to what? 1. But for heteronuclear atomic molecule, y upon x is always greater than 1. And therefore, the higher the value of this ratio, greater will be the polarity. As the ratio increases, as the value of this goes on increases, obviously polarity also goes on changing, also increases. So this is how the comparison we discussed today in molecular orbital theory. So I appeal to all the students to read all the content of this topic, because comparison is easy, but this comparison helps to understand the MOT of both homo and heteronuclear atomic molecules. So we'll discuss in next video lectures about same. Bye.